Dear students, this is the third lecture related to Introduction to Electrodynamics, and this short lecture is to introduce the basic equation of electrodynamics called Maxwell's equations. These four Maxwell's equations are evolved from the basic equations of electrostatics and magnetostatics that we have discussed in our earlier lectures 1 and 2. These four equations are obtained by modifying the static field equations by incorporating the effects of time-varying sources. And we can see that these four equations are the foundation stones of the entire electrodynamics or electromagnetic theory. Any problem in electrodynamics or electromagnetism can be easily solved based on these four equations or starting from these four equations. In that respect, these four equations are of much importance. So let us check how these equations are evolved from static field equations. We have introduced the electrostatic problem as a cause-effect principle with the stationary charge ρ as the cause of the electrostatic field E or D. In the case of free space it is E, and in the case of a material medium it is represented as D. Similarly, in magnetostatic problem also, we have introduced the effect due to a magnetostatic situation. That is, the effect is the magnetostatic field, and the cause of that effect is the static current or steady current J. And in that respect, both electrostatics and magnetostatics, we have considered it as a cause-effect principle, and the ultimate aim behind any electrostatic or magnetostatic problem is to evaluate the effect due to the cause. In a similar argument, we can see that the electrodynamics or electromagnetism also can be represented as a cause-effect principle. In this situation, the cause is a time-varying source, that is both ρ and J. Both ρ and J can be considered as the source of the electrodynamics, time varying with respect to, it is changing with respect to time. And the effect is both electric and magnetic field simultaneously coming into picture. That is, in the case of free space, we have E and B, and in the case of material medium, we have D and H. So that is, for the case of electrodynamics, the source is a changing current or a changing charge, both equal to a time-varying source. And this time-varying source produces both electric and magnetic field simultaneously. So the cause-effect principle can be extended to electromagnetism also. And the ultimate aim behind any electromagnetic problem or electrodynamic problem is to find out the effect due to a time-varying source, and the effect is the electric field and magnetic field. And after evaluating both electric and magnetic field, we are able to find out the power or the energy associated with that electromagnetic situation also. Now, in the case of stationary charges, we have represented the charge as, or general form of the charge is taken as rho of r dash. The source is taken at coordinates x dash, y dash, z dash. And the field is taken, the field point is taken as p of x, y, z. That is, the source is at the primed coordinate x dash, y dash, z dash, and the field is with respect to x, y, z. So that is represented by E of r. So the effect is at r, distance r from the origin, and the source is at r dash from the origin. The r dash in this case is a volume charge, and we have to change x dash, y dash, z dash in order to consider different regions of the volume charge. The associated potential in this case is V of R. Okay, so that is with the static situation of electrostatic. In this case of magnetostatics, we have the source is represented at R dash with J of R dash. And the effect is V of R. That is a static current J of R, and the static magnetic field B of R, or the static vector potential A of R. Now, in the case of electrodynamics, the source term changes with the time. So it is represented with j of r dash t. The position is quite same, that is r dash, and its magnitude is changing, so j of r dash t. Or we can consider a source as rho of r dash t, that is at a particular position a charge is placed and that is changing with respect to time. And what happens if the source in the form of a steady current or a changing current or a changing charge presence? It produces both electric and magnetic field. Later we can see that it is based on the Faraday's law and Ampere's law. And we have to evaluate both electric field quantity E of R, RT, and B of RT. That is E of RT and B of RT. And the associated quantities, the potential quantities A of RT, and B of RT. So any electrodynamic problem can be considered as a problem to evaluate the electric field and magnetic field at a destination due to a changing source. Now coming to the potential situations, potential equations. We have the relation connecting electric field and potential for the stationary charges for the case of electrostatic condition as E of R is equal to minus del V of R. That is, electric field at the field location E of R is equal to the negative gradient of potential V of R. And the case of magnetostatics also, we have B of R is equal to curl of the vector potential A. B of R is equal to del cross A of R. And in the case of electromagnetism, these two equations are modified. We have to modify these two equations by incorporating the effect of time also. And in the first equation, the electric field is represented as E of RT instead of taking it as E of R. Since it is electrodynamic problem, E of RT is equal to minus del V of RT plus an additional term, that is minus dou A of RT by dou T. A of RT by dou T, that is a change in vector potential. So this is the modified vector potential relation connecting electric field and the potentials. We can see that along with the scalar potential, the vector potential also is coming into picture, and that depicts the presence of both electric and magnetic field simultaneously with respect to a changing source. And coming to the magnetic field potential relation, that is del cross B is equal to del cross A is equal to B, we can see that there is no change for that equation, that is B of RT is equal to del cross A of RT. So actually in static conditions, even though there is a suffix E of R is equal to minus del V of R, we simply write it as E is equal to minus del V. No need to represent the suffix R. Similarly, B is equal to del cross A. That is understood. And in the case of electrodynamics also, it is understood. So we write it as E is equal to minus del V minus dou A by dou T. So no need to write the suffix R and T always. Or B is equal to del cross A. Both equations in the magnetostatics, B is equal to del cross A and B is equal to del cross A. Both are same in appearance, but we can see that they are not identical because it is a changing potential. This vector potential is changing in electrodynamic situation, whereas in static condition, the vector potential remains as such. Now let us refresh our knowledge about the static field equations in this slide. See, the first equation is based on Gauss law, Gauss flux theorem in electrostatics, that is total normal electric flux over a closed surface is equal to 0. And while discussing Gauss flux theorem, we have considered the source as rho. The rho is a free charge. In electrostatics, we always deal with the free charges. Rho is usually represented as rho, but it is rho F. That is free charge. In order to consider it as a free charge, rho F. When coming to the picture of a material medium, there is a possibility of another type of charge called bound charges. So rho is equal to rho F plus rho B. This rho F stands for free charge and rho B for bound charge. Bound charge produced by polarization. When the material is placed in an external field, polarization takes place. So negative and positive charge concentration or accumulation is produced on the dielectric medium. So that also causes some electric field concentration. So it is called rho B. So in this equation del dot D, even though I have written it as rho F, this is equal to rho F, rho. That is rho means rho F. Now correspondingly del dot D is equal to rho by epsilon 0. This may be equal to rho F by epsilon 0. This was our earlier equation, and now it is del dot D is equal to rho F by del dot D is equal to rho. The equation, there is no change for the equation when we discuss this equation in the case of electrodynamics also, that we will come in consider in the next slide. So this is the static field equation for Gauss Flux theorem. Then the integral form of that equation is closed surface integral d dot ds is equal to volume integral rho f dv, or simply rho dv, or closed surface integral E dot ds is equal to 1 by epsilon 0 volume integral rho dv, that is 1 by epsilon 0, that is closed surface integral E dot ds is equal to 1 by epsilon 0 volume integral rho dv. Now the second equation is the conservative nature of electrostatic field. That is the curl of E. Curl of E is equal to 0. That is, in this case we have E of R. In the earlier case it is D of R. D of R. Here it is E of R. Del cross E of R is equal to 0. Or closed line integral E dot dl is equal to 0. That is the conservative nature of electrostatic field. That is, curl of electrostatic field is equal to 0. Now the third equation is Gauss law for magnetism, or non-existence of a magnetic monopole. That is, always a magnetic pole exists in the form of pair. Along with the north pole there will be a south pole. So non-existence of magnetic monopole is the Gauss Flux theorem for magnetism, and the differential form of that equation is del dot B is equal to 0, del dot B of R is equal to 0, and closed surface integral B dot ds is equal to 0. Now in the case of a source-free equation, that is for just like del cross E is equal to 0, del dot B equal to 0, we are representing the field quantities used for the free space medium, that is E and B. Whereas in the case of a dielectric medium, where some source is coming into picture, that is for the electrostatic, the static condition, there is source rho. In that case we represent it in terms of the vector D. Del dot D is equal to rho F. Usually we take this form. Instead of considering this del dot D is equal to rho by epsilon 0, the common method of representation of this equation is del dot D is equal to rho F. But not del cross D is equal to 0, not necessary, because there is no source term is coming. Or del dot H is equal to 0. No need to write this also like that, because there is no source term. But coming to the fourth equation, that is Ampere's law. Ampere's law is in terms of the source Jf. As in the case of the electrostatic condition, this Jf simply J. It is equal to J. That is free current. In dielectric material, due to polarization, there is a possibility of rho B. Similarly, in the case of a magnetic material, due to polarization, there is a possibility of bound currents also. The magnetization produces some currents inside, that is called bound currents also. So that bound current, the effect of bound current is incorporated in the vector H. So we are writing this expression as del cross H is equal to Jf, or del cross B is equal to mu 0 Jf. No need to write it in this form. This will do. So del cross H is equal to Jf. That is enough. So it is equal to closed line integral H dot dl is equal to surface integral Jf dot ds. This is the integral form of this equation. Now coming to the time dependent terms associated with these equations. So what happens to these equations when we are dealing with a change with respect to the time factor. The first equation, here we have it as del dot E of R is equal to rho of R dash divided by epsilon 0, and del cross B of R is equal to 0. This equation changes to del dot E of R T. E of R T is equal to rho by epsilon 0, or del dot B of RT is equal to 0 in the case of time varying situations. There is no change for the nature of the equation, but the equations remains as such, but the quantities changes. E of R changes to E of RT, rho of R dash changes to rho of R dash T divided by epsilon 0, and B of R changes to B of RT. And the other equation, del cross B is equal to 0, and del cross B is equal to, del cross E is equal to 0, and del cross B is equal to mu 0j. This equation, del cross E of R is equal to 0, del cross B of R is equal to mu 0j of R dash. And this changes by adding another term with the help of Faraday's law. We have to add a term here like this, minus dou B by dou T. So this is Faraday's law. Minus dou B by dou T, that is del cross E of RT changes to minus dou by dou T of B of RT. Similarly, the other equation changes with the addition of a new term called displacement current term. Displacement. So we are familiar with currents like conduction current, polarization current, magnetization current. That is conduction current due to movement of actual charge carriers, that is movement of electrons or positive charges through a conductor. Electrons are moving, that produces conduction current. In the case of a material, when it gets polarized, that means there is some alignment takes place, electrons adjust here and there, and that produces a current that is called the polarization current. In the case of magnetization also, there is a reorientation of the orbiting electrons, so that there are also some changes taking place, that movement of electrons taking place, that is called the magnetization current. Now we are introducing another type of current that is called the displacement current, and the displacement current is a current originated with respect to time varying effect of the electric field or electric flux. When the electric field quantity associated with some region is changing with respect to time, we can say that is equivalent to a current called displacement current. And this current term is actually introduced by Maxwell, and a modification for Ampere circuitry theorem is made by Maxwell, and the Ampere theorem is hereafter termed as Ampere-Maxwell equation. So the equation corresponding to this one changes to del cross B is equal to mu 0j plus dou D by dou T. B of RT is equal to mu 0j of R dash T dou by dou T of RT. So such a situation we have to some modification is needed. So let us consider these equations once again. The first equation, that is Gauss Flux theorem, there is no change taking place. No change. Del dot D of R is equal to rho of R dash, rho F of R dash changes to del dot D of RT is equal to rho F of R dash T. Then the second equation, there is no change. The divergence equation, del dot B of R is equal to 0 for static condition, changes to del dot B of R dash, del dot B of RT is equal to 0 for time varying situations. And the third equation, del cross E is equal to 0, that is del cross E of R is equal to 0, changes to del cross E of RT is equal to minus dou B by dou T. That is, in this case, this case is for electrodynamic situation, and the first case, this is for electrostatic situation. And electrostatic situation, there is only variable R, and here we have R and time, and the source term in this case is electrostatic situation. It is R. Now source term, it is R dash and R dash, and here it is R dash and time. Okay, now coming to the fourth equation, that is del cross B is equal to mu 0 j. Mu 0 j. This equation changes to del cross B is equal to mu 0 jf plus mu 0 epsilon 0 dou E by dou t. That is the additional term that we have considered just now, the displacement current term dou D by dou t. That is the expanded form is epsilon 0. This is epsilon 0 dou E by dou t. Epsilon 0 dou E by dou t is called the displacement current. And that term also is coming into picture. So this is the modified form of the static field equation. That is, Ampere's law is modified into Ampere-Maxwell equation. So the four Maxwell's equations, the differential and integral forms can be considered once again. The Gauss law in electrodynamic situations, del dot D is equal to rho f, that is del dot D of RT. Del dot D of RT is equal to rho f of R dash T. Or closed surface integral D dot ds is equal to volume integral rho f d tau or dv. That is the Gauss Flux Theorem equation. Then this is Faraday's law. Then the second equation, del cross E is equal to minus dou B by dou t. Or closed line integral E dot dl is equal to surface integral minus dou B by dou t dot ds. Faraday's law. Then Gauss law for magnetism, that is del dot B is equal to 0, or closed surface integral B dot ds is equal to 0. That is the third equation. Then fourth one, Ampere-Maxwell law, del cross H is equal to Jf plus dou D by dou t, or closed line integral H dot dl is equal to surface integral Jf plus dou D by dou t dot ds. So these four equations, these are the four equations related to electrodynamics, and these four equations are the fundamental equations of electrodynamics called Maxwell's equations. So as I have mentioned, these four fundamental equations are of much relevance in the case of any problem related to electrodynamics or electromagnetism. Any problem, we are able to start with these four equations. Along with the helping tools that we have considered, the two potential relations, that is del E is equal to minus del V minus dou A by dou t, and B is equal to del cross A, along with the boundary conditions also that we will consider in the coming lectures in detail. So with the helping tools, potential formulation and boundary conditions, we are able to solve any problem starting from these Maxwell's equations in the case of electromagnetic theory or electrodynamics. Any complicated problem in communication electronics, just like the communication principles based on optic fiber communication or microwave communication or radio wave communication, satellite communication, or some other applications like ISM, industrial, scientific and medical applications of electromagnetic waves, the research purpose. Everywhere we are making use of these four equations and the associated propagation equations. So these equations are of very much importance. So let us study these things thoroughly with respect to how these equations are transforming from static field equations to dynamic conditions. Okay, thank you very much.